Okay, we're going to talk a little bit about other frictional forces other than surface friction. We talked about static friction and kinetic friction of surfaces. And I'm going to go through this fairly quickly because most of the classes don't cover this for Physics 1, but we're going to do this anyway. So this may be an optional section for your particular class. But in any case, forces of friction, we talked about surfaces will provide resistance against motion, but also traveling through a viscous medium, there's going to be resistance to motion. What happens here is as we travel through a viscous medium, we're displacing different atoms or different molecules. And when we do so, they have a cohesive force. They want to pull together, so we're pushing them apart. And we have to do work in order to do that. So this resistance that we run into of these microscopic particles is what we call drag. And we briefly talked about it with planes. Um, the biggest takeaway from this is drag is very, very difficult to model. Okay, we can model surface friction very easily because we just say, oh, what's the normal force? What's the coefficient of friction? Is it stationary, static? Is it moving, kinetic? That's fine. Here, the way the particles move, sometimes it will be organized, what we call laminar flow. Sometimes it will be chaotic and what we call, well, it's turbulent flow. We have vortices. I shouldn't use the term chaos too much. But depending on what type of flow is going on around the object in motion, that is going to affect the drag. And normally drag either is proportional to the speed or the speed squared. So, it's a very, very complex type of interaction that we have difficulty coming up with good equations to model it with. When things go slowly, if the viscosity is low, generally we get what's called laminar flow. The fluid will flow around the object where every molecule will follow a very well-defined trajectory, what we call streamlines. But as we get going faster and faster, what begins to happen is some of the fluid begins to rotate. Now, again, every particle in a streamline that passes a particular point will go through exactly the same trajectory. We call it streamline flow, we call it laminar flow. And what's interesting is, you think that we get more drag from turbulent flow than streamline flow. But actually, there are different situations where streamline flow can be better and where turbulent flow can be better. So streamline flow, here's a car. They're doing a wind tunnel test with smoke, and the smoke follows the streamlines. You can clearly see that the particles get out of the way of the car pretty well. Now, so for some objects, streamline flow reduces drag. For other objects, turbulent flow actually separates the interaction of the fluid with the object traveling through it. So that can create a decrease in drag. So again, it's very complex, and we're not going to spend a tremendous amount of time here. Here you see a combination of streamline flow around this ball and then some turbulent flow with vortices behind. And again, we generally tend to see turbulent flow show up once we exceed a certain velocity. And the critical velocity at which turbulent flow shows up will go down as the viscosity goes up. Okay. And again, you can see turbulent flow. This is a fan blade that's rotating above a candle. So it's called a Schlieren photograph. It's a really cool photograph where it looks at very subtle changes in the index of refraction. As the air gets heated up, there's a change in the index of refraction here. But again, you can see how the air rotates there. Very, very well defined. So again, here we can imagine a ball traveling through the air and these vortices starting up behind it. So again, viscosity is really a measure of the internal friction in the fluid. The greater the viscosity, typically, the greater the cohesion between the molecules, because um, if you're causing a fluid to flow, you're causing the molecules to move with respect to one another. And if they're cohesive, they like to stick together, they're going to resist that type of motion. Now, air has a very low viscosity. There aren't really many molecules in air, so there's not really much to interact, or the air molecules are very spread apart. Water has more viscosity because the water molecules have these hydrogen bonds that cause them to be cohesive. But if you really want a cohesive fluid, we can go to the extreme of adding sugar molecules. And sugar molecules, are organic, but they have polar and non-polar ends, so they really like to stick to one another. So if you add a lot of sugar to something, such as the case of molasses, you can get a really, really high viscosity. There is something called Reynolds number. And again, you're talking about drag is it's complex process. So we'll do more conceptual things right here. But there is something called Reynolds number that you can calculate based on the density of the material, the speed at which an object is traveling, the diameter of the object, and then finally, this right here is the viscosity. Okay, so the Reynolds number is useful because it tells you when streamline flow ends and when turbulent flow starts beginning, and when turbulent flow is really dominant. Typically, if everything is to scale here in terms of units being all SI or all CGS, below 2000 for Reynolds number, you're typically going to just get streamline flow. Above 3000, you're going to get a pretty dominant turbulent flow. And here we can see laminar flow, or Reynolds number is well below 1000. Then you can see turbulent flow, or Reynolds number is way up there. Now, what's interesting is adding to the complexity here, the surface texture of an object will greatly influence the drag. And what's weird is that a rough surface will sometimes be better than a smooth surface. Here we see the coefficient of drag for two balls, a smooth ball and a rough ball. And for most lower speeds where the Reynolds number is low, we are getting, fairly good laminar flow, laminar flow, laminar flow. We exceed about the 2000, 3000 threshold right here. All of a sudden the flow starts getting turbulent. Now what happens is with the rough surface is it actually lets the turbulent flow separate from the surface sooner. And with a roughed up ball, like dimples on a golf ball, felt on a tennis ball, will actually drop the coefficient of drag sooner than it will for a smooth ball. So golf balls have dimples because at the speed that they travel at and the Reynolds number that they have, given a particular velocity, they'll travel better due to these dimples or this roughed up surface. Same thing with the tennis ball. They're right in this domain right here. Okay? The smooth ball gets going faster and faster than the smoother surface. Again, the drag is reduced. Now, this is a coefficient of drag. It doesn't mean that the drag is becoming less. The coefficient of drag is multiplied by either V or V squared. So the drag is actually going up, but it's not going up linearly or parabolically, if you will, for these different values of CD. Okay, so a lot going on here. And again, Here we can see that right there. A dimpled golf ball travels farther than a smooth golf ball. You can see again, here's a smooth surface versus a rough surface. You see, because of that separation, you don't get as large of a wake, okay? Less drag. So, we look at different things, race cars, bobsleds, aerodynamic shaping, and what the surface is made out of is so crucial to reducing drag, because it is such a complex interaction. We really have to use computers to model it. We can't just do a quick calculation and say, well, this is going to go better than this. That's why we had to build wind tunnels. If it were as easy to just solve some simple equations, that would have been great. But again, drag is a very, very complex interaction. And wind tunnels have to be used to make sure that our computer models are valid. And they do show the drag that we expect for the particular speeds that we expect. And here's Michael Phelps. You can see the bodysuits that they use for swimming. And these, again, were actually textured suits that were tested and found to be create the least amount of drag. Actually, 10% less drag. I was one of the few members of my family who didn't really stay on a swim team for very long. And I remember my brother swam competitively in college. And yeah, some of the real hardcore people who swam, even the guys would shave their bodies and shave their heads to get the reduce as much drag as possible. It's really, taking the physics to the extreme. Fall is coming. Canada geese, not Canadian geese, Canada geese. They migrate southward during this time of the year, and they fly in a V formation because the bow shock, it's not a shock, the bow front of the air that displaces actually makes it easier for all the other geese to fly. So through evolution, they've basically learned this. They've basically taken this up as an instinct, and this reduces how much energy they need to expend during migration. So here we go. Here's the equation for drag. And again, this equation has v squared in it. So this is primarily laminar flow, okay? So you can see that that drag coefficient does depend on velocity and Reynolds number and all that other crazy stuff. But generally, the coefficient of drag times the viscosity of the fluid times the cross-sectional area of the object. And by the way, the coefficient of drag is dependent on the shape too. Don't think you can throw any shaped object in there and get the coefficient of drag to be the same. But again, when something is falling, the gravitational force is opposed by drag. And when something is falling, eventually it'll reach what's called terminal velocity when the net force goes to zero, okay? And again, that depends on the shape of the object, the viscosity of the fluid. That's why when you drop something in water, it'll reach some velocity and just hit toward the bottom at a fairly constant rate. If you drop something in the air, it takes a long time to accelerate before it reaches terminal velocity. Again, the shape really affects the coefficient of drag. And here's some drag coefficients for different shaped objects. You see, obviously, a flat object has a bad coefficient of drag. Rounder objects have a lower coefficient of drag. And a nice streamlined body, look how low that coefficient of drag goes. So that's why things are shaped the way that they're shaped. And again, once the force of drag becomes equal to the force of gravity, The object is now in dynamic equilibrium, okay? And the velocity will not go any faster, and we call that terminal velocity. The terminal velocity is equal to the square root of 2 times the weight, okay? So the heavier something is, the faster it's going to fall with air resistance. I know Galileo said everything accelerates at the same rate. If you eliminate air resistance, now we're saying air resistance is here. So heavier objects fall faster, okay? And if we increase the coefficient of drag, we increase the density of the fluid, we increase the area, we go faster. I'm sorry, we go slower. Sorry about that. These are some terminal velocities of selected objects. A 16-pound shot, if you ever did track and field, you know what this is. Big metal iron ball. And if you drop that, that thing is not going to reach terminal velocity for a long time. It will reach about 325 miles per hour before it slows down, okay? That's going to do some damage if you drop it out of a plane. But we see other things. You throw a football, there's a limit to how fast that football is going to go, you know, because of the drag. Baseball, and this is surprising that baseball actually has a lower terminal velocity, but the reason for that is the football is more aerodynamically shaped. There's a golf ball, softball, tennis ball, soccer ball, basketball, bigger area, okay, volleyball, and a ping pong ball, okay. So this explains terminal velocity. If you jump out of a plane without a parachute, you will reach terminal velocity. You will also be terminated because your terminal velocity is about 50 meters per second. Even putting your arms out and your legs out, you can't slow down. You're going to hit the ground at over 100 miles per hour. But by creating a large surface, making that A very, very large, remember, terminal velocity depends on that A down here. If we can make a huge surface, like in a parachute, we can bring that terminal velocity way down. And you can see here, this terminal velocity is about 8 meters per second. Still, you're going pretty fast. You can hurt yourself, you know, about 17 miles per hour. But, you know, skydivers will also, you know, use lift and actually slow themselves down even more. So there's also something called Stokes' law for round objects. The force of drag for a round particle is 6 pi times the radius of the particle times the viscosity times the velocity. So that when we calculate terminal velocity from this, we can see that different particles will settle out at different rates, okay? This is very important because larger particles, if you shake something up, they're going to settle first, and the lighter particles will settle last. And it's also the reason why we need to use a centrifuge to separate particles sometimes, because what we call Brownian motion, molecules just being jarred thermally, will keep particles suspended. Okay. Also, some particles are ionic, so that'll contribute to staying in suspension. But if you can increase the acceleration beyond the acceleration of gravity, you can increase their terminal velocity and have them settle out, again, according to particle size. Okay.